In the last lecture, we talked about Grothendieck categories. Yeah, they are the categories which have all the nice properties of the category of abelian groups. And then some examples like abelian category of abelian groups, category of modules, and some other categories like sheaves of abelian groups on topological spaces or on a Grothendieck site, or quasi-coherent sheaves on a scheme. But then we said that well, we want to construct more Grothendieck categories from the existing ones, and one good way of doing that is localization. Now we construct some localizations are like quotients at the level of categories. You are identifying lots of objects and maybe making some morphisms invertible. So this, after studying localization via left multiplicative systems or Serre subcategories, I just want to remind you that for Serre subcategories, when we do this MS, there is yet another way of defining the localization, where you change the objects rather than just changing the morphism sets. But anyway, coming back to this, like coming back to Grothendieck categories, every Grothendieck category with a generator can actually be presented as a localization of a module category over a commutative ring. Yeah, so this is what Gabriel-Popescu theorem said. So if we know all module categories and all their localizations, then that's the entire class of all such nice categories, of all such Grothendieck categories. So now today our first job is to look at some of the properties of Grothendieck categories. Okay, so for example, the first property, if A is Grothendieck, then I'm not going to give any proofs. The proofs will be very long, but there are some very nice properties. So first one is that A has an injective cogenerator. Okay, so what is the meaning of injective? Injective is the dual concept to projective. So it says that, let me write this for you, that whenever you are given an inclusion I can write it like this, and then object I is said to be injective if whenever the row is exact, then for all such things there exists this. There exists an arrow such that the diagram commutes. Okay, this is injective object. And the dual notion is projective, so I is the injective object here. And what is the meaning of cogenerator? Cogenerator is the dual notion of generator. Last time we saw what a generator is, so injective cogenerators exist. And some examples we can definitely give. Cogenerators, just like generators, if they exist, they are not necessarily unique. There can be multiple such cogenerators, but we still have to write some examples. So Q mod Z for the category of abelian groups. Then if you want to talk about the category of rings, then you have to take the abelian group homomorphisms from R to Q mod Z for R-ab or the category of left R modules. So you still have to verify these things, but it indeed works. And this is an injective cogenerator, and then the localization, I'm not going to talk about it directly. You will use this injective cogenerator in, and maybe you will take the image under localization functor, the reflector. Okay, second thing, every element, every object A of A has an injective hull. Okay, so this is an important notion of injective hull. The dual notion is called projective cover. So what is an injective hull? Like the definition I should tell you that for any, that means there exists an injective, I shouldn't say injective, a mono A to E, let me call it M, such that for any subobject E prime to E, I should say first such that maybe I will write the list properly. First thing is that E is injective. So any object can be embedded inside an injective object in a minimal fashion. So what is the meaning of minimal? That whenever A can be embedded inside any other injective object, then there will exist an embedding from E to that injective object, such that the diagram commutes. So it's universal, the minimal way. But in algebra, we usually use a slightly different terminology. The second one, I can say that the image of M is an essential subobject of E. Okay, so what is the meaning of essential here? Essential means it intersects any other non-zero subobject, i.e. The intersection is what? Pullback, i.e. for any monomorphism E prime to E, let me call this M prime. If you take this image of M, so I will denote the image object by this and the image morphism by small im to E, and then E prime is sitting here, and then if you take the pullback of a mono is mono, so I can write these two as monomorphisms. So this P is also a subobject, via either of the sides of the rectangle of the commutative square. So for any this, if P is 0, then E prime is 0. So what I am saying, that if E prime is non-zero, then it intersects non-trivially with the image. You get the idea? That we are trying to touch everything essentially. Every submodule, every non-zero submodule is touched by this embedding of A, image of A inside. You can also think about elements. Why, I will make it clear very soon, why we can talk about elements here. Okay, then the third property, which is essential, which is a property of all Grothendieck categories, is that it is well powered. Do you remember what I mean by this? Well powered means the collection of subobjects, the isomorphism classes of monomorphisms with the same target. We defined some order relation on subobjects of a fixed object, and then we quotiented out by less equal intersection greater equal. Yeah, so that collection is a set. Okay, so A is well powered. Then a very deep result, and if A is well powered and the definition is more or less self-dual, yeah, so therefore the quotient objects of a fixed object are also going to form a set, because kernel and co-kernel, that provides a bijection, we have seen that. Okay, so then another deep thing is that A is complete. Second point, like essential subobject. Okay.
We can use that for R modules.
R modules.
Every R module will be embedded in.
So I can definitely give you a direct example. So do you know that any free module is projective? Yes, free module is projective. So given any module, you can always take projection from a free module. Yeah, there exists an epimorphism from a free module onto a given module when we are working over a concrete ring. Now just take the dual category. Then you will get an injective cover, in injective hull or injective envelope.
So you're saying that free modules form a projective cover?
Free modules are projective covers. I mean, you have to take the smallest free module, you take the generating set appropriately, and then you map it. Yeah, so I
don't understand what this property is saying.
This property is saying that the module in which we are embedding, the injective module in which we are embedding the given module, that's not too large. So, okay, we will talk about projective modules soon. Maybe I will elaborate on this later. Right now my purpose is just to write these things. Yeah, so we will see that any direct sum of projectives is again projective. So similarly for injectives also the same thing will happen. So therefore you can embed one injective module into another injective module as a direct summand. So every morphism with domain injective, sorry, every injective morphism with domain, every monomorphism with injective domain splits. Yeah, so therefore the target is always a direct sum of this E with something else. So we are able to choose the least such. That's what this condition means. I haven't said all these things, so maybe we will delay it a bit. Hopefully towards the end of this lecture we'll come to projective objects and injective objects. Okay, one very deep property we only assumed as part of AB4 condition, that the Grothendieck category has arbitrary coproducts. So it was co-complete. But as a result of all the conditions, you can actually show that it is complete. So all the products also exist. And this is not an easy statement. Only products were missing, so they also exist. Okay, then A is locally presentable. So locally presentable, I am not saying locally finitely presentable. Locally kappa presentable for some cardinal kappa. So the kappa presentable objects, they form a set for some kappa, and every object can be written as a directed colimit of a diagram of kappa presentable objects. Okay. And the sixth property is that whenever, like if a functor f from A to B, sorry, a functor, I should just say a functor f from A to B has a left adjoint if and only if f preserves all limits. So, I mean, maybe I should call it, like, just to be consistent with our previous notation, I should say that G from A to B has a left adjoint if and only if G preserves all limits. What theorem are we stating here? Adjoint functor theorem. Yeah. And there are some more conditions. We are not using the primeval form, but we are using either general or spatial. If you remember the statement, then you will know which one. Yeah, it's an if and only if statement. Then either the solution set condition or this well powered and other part, that has been already checked. So therefore, adjoint functor theorem takes a very simple form. Yeah, that G preserves limits if and only if it has a left adjoint. So it's very easy to work with such categories comparatively. Well, okay, so Grothendieck categories are nice. It has got very nice properties. What do we do with them? Yeah, and how do we use it? So before I move ahead to a new topic which is relevant, can I ask you to give an example of a small abelian category? The examples that you have seen so far are the category of abelian groups and the category of R modules and their localizations, but they are all large categories. Can you give me an example of a small abelian category? Abelian categories are finitely complete and finitely co-complete. Yes, you wanted to say something, or you? Terminal category, zero category. Yeah, zero category is, yes, it is. But some interesting examples. Okay, so a small abelian category, and an example of a this is a question which not many people think about. Yeah. So take any, I mean, I will give that example at the end. So let R be a unital ring and consider R mod to be the full subcategory of this consisting of finitely presented objects. Okay, so finitely presented modules. Do you know what finitely presented module is? So recall that M in RAB is finitely presented if the home in this category, in the category of R modules, from R to blank, like home R blank, from R, from this category of functors to the category of abelian groups, it preserves filtered colimits or directed colimits, or equivalently that module is finitely generated and finitely presented. So finitely generated and finitely related. So there are finitely many generators and finitely many relations. This is the algebraic definition, but this is the category theoretic definition. We looked at it while studying locally finitely presentable categories. So this is R with little mod, little m. Okay. So in general, this category has got byproducts. If you take finitely presented modules, then their direct sum is also finitely presented. Then it has co-kernels, but it lacks kernels. Yeah, so R mod, I mean usually R mod has byproducts, finite byproducts and co-kernels, but may lack kernels. However, if you consider your ring to be a spatial ring, but if R is Noetherian, for example, Noetherian, Artinian, a field, a PID, yeah, if you know these terms, then R mod is closed under kernels. And hence is abelian. So now you have several examples of small abelian categories. Okay?
This is a stupid question, but can we take like finite abelian groups?
Finite abelian groups?
Yeah.
Finite abelian groups, are they closed under direct sums? Yes.
Countable abelian groups.
No, finite also will make sense. Finite abelian groups, the kernel.
Generates and co-generates.
No, but even finite abelian groups, that will be an abelian category. No, but we are talking about finitely presentable. So finite abelian groups are finitely presentable, but there are obviously infinite abelian groups which are finitely presentable.
Since we are talking about smallness,
Yeah,
that will be
that will be an example. Yeah, smallness. So finite abelian groups are definitely closed under kernels. Kernels are obviously subobjects. Subobjects of finite abelian groups are again finite. Quotient objects of finite abelian groups are finite, and direct sum of two finite abelian groups is again finite. So finite abelian groups will also make sense. Yeah, and finitely generated, or finitely presented will also make sense. Okay. So yes, this category is closed under kernels and hence is abelian. So you have got plenty of examples of this. I mean, in particular, finite dimensional vector spaces. Yeah, they form a category isomorphic to the category of natural not natural numbers, but we have seen that. The mod k, we have seen that example at the beginning of the course. Dimensions, it is equivalent to that category. Okay. So now why did I mention this? Because I want to talk about a very important theorem, and in the hypothesis of that theorem I am going to assume that this category is small abelian. Then your natural question would be, what are small abelian? Like, what are some examples of small abelian categories? So I already provided you some. Another thing you should remember is that given any abelian category and let's say a set of objects, you can always close it under direct sums. You can always close it under kernels, you can always close it under co-kernels, and then again their direct sums and their kernels and their co-kernels. So you can generate a small abelian category out of a given small collection of objects. It will be a full subcategory. So that is always possible. So at a time, if you are only talking about, let's say, finitely many objects, then this particular diagram or this particular system will always live in a small abelian category contained inside the given abelian category. So you always have plenty of examples at hand. Okay, so now this is a very interesting and extremely powerful theorem. This was proved by Peter Freyd and Mitchell. Okay, so this is called Freyd-Mitchell embedding theorem. Let me first state the theorem and then I will tell you its significance. If A is a small abelian category, then there is a unital ring R and an exact functor F from A to the category of R modules. I mean exact fully faithful functor, yeah, I mean and a fully faithful exact functor, maybe I should add that. Okay, now before I tell you the sketch of the proof, yeah, I want to emphasize on what's really happening here. It's about universality of module categories. Module categories over only a single object pre-additive category. Yeah, R is a ring in the standard algebraic sense. So what we are saying that every small abelian category can be embedded inside such a thing in a fully faithful manner via an exact embedding, which means we can treat the objects of this small abelian category as if they are modules and the morphisms between them as if they are morphisms between modules. And what is the benefit of working with modules? That you can access its elements. So therefore, lot of properties that we are proving, you can actually use elements in those proofs. So after proving this theorem, I am going to give you two examples. One will be the so-called 5 lemma and the second one will be snake lemma, and I have chosen to give one proof via the classical diagram chasing only arrows, and the second proof I will do via elemental diagram chasing. Okay, so that's why this is very important. Okay, so you already have plenty of examples of small abelian categories to understand the importance, and let's look at the proof. First of all, whenever you are given A, any small abelian category, and you think about a fully faithful embedding into some category, what do you think of? Yoneda. Okay, good. So everybody is awake. So consider Yoneda embedding Y from A op into A ab. Okay, all the A modules. It's a small category, so I can say it's an A module. Okay, small category, small pre-additive category, what do we know? What do we call it? A ringoid or a ring with many objects. So in particular, A is like small abelian implies small pre-additive, so it is also a ring with many objects. Okay, so the image, I have considered A op, but we can also take op on the opposite side and not take it on this side. So this factors through lex functors from A to ab. What do I mean by that? Yeah, I simply mean that the representable functor is actually, I mean, it preserves limits. Yeah, since home functors are left exact. So obviously I can say that home functors always preserve limits. So what is the embedding here? You tell me. An object is mapping to A blank. Yeah, so this is the covariant home functor. So covariant home functor preserves all limits, so therefore it factors through lex. And lex AAB is a full subcategory of AAB. Yeah, so recall that lex AAB embedded inside AAB has, I mean, is fully faithful and admits an exact left adjoint. What do we call such exact left adjoint? Left adjoint is always right exact, but I am claiming it's also left exact. What do we call such a thing? We saw this last time. Fully faithful embedding, it has a left adjoint. What do we call such an adjunction? Reflection. Very good. And when the left adjoint, in addition to preserving all co-limits, if it also preserves finite limits, then what do we call it? It is called localization functor. Okay. So, and therefore, lex AAB, I mean, we saw this already, is a localization of the category of A modules, AAB, and hence is Grothendieck. Yes. So every localization of a Grothendieck category is again Grothendieck, and in fact every Grothendieck category is a localization of a module category. When we saw that statement, we also saw this particular example. Okay. Moreover, the co-restricted means the codomain is restricted. Co-restricted Yoneda embedding Y from A op to lex AAB is exact. Well, this is something you need to check. The original thing is exact, so the co-restricted thing is also exact. Okay. So, now we said that lex AAB is Grothendieck, and then the first property that we stated today for a Grothendieck category was that it has an injective cogenerator. Okay. So hence is Grothendieck. Let C be an injective cogenerator for lex. It's not unique, but you choose anything you want. Okay. Now to finish off the proof, let R be the set of functors, set of endomorphisms of, maybe I will call it I will give it a notation, yeah, L equal to lex AAB. Yeah, so I'm calling it L, and then let R be the set of endomorphisms from C to C in L. Be a unital ring. Then what will happen? Yeah, because it is an injective co-generator, we use this dual trick in Gabriel-Popescu theorem. If it is a generator, then the home functor is fully faithful. Now here the dual home functor is fully faithful. Yeah, then L op into RAB. What does this functor do? It takes an object. This functor is defined by L blank C. Okay. So this functor, then this is fully faithful because it's an injective co-generator. You need both properties, that it is injective and it is co-generator. Then only you get this. Okay, so now combine this data. What did we say? Y is an embedding from A op to AAB, but it factors through lex L. Yeah, so combining, what do we get? Let me write it. A, then you have AAB op. This is our Y, but it factors through L op equal to lex functors from A to A op. Yeah, it factors through this embedding. This one has a left adjoint, and then this L op embeds inside RAB, and that's our proof. The horizontal embedding is our embedding into a module category appropriately. So we don't really have to work with rings with many objects. You can as well work with rings with one object. That's what this Freyd-Mitchell embedding, in addition to working with concrete elements, because every object of the small abelian category is in fact just a module. Yeah, so this is the main advantage of doing this, and this embedding is fully faithful, so you don't really lose any data. Whatever you had earlier, and it's exact as well. So which means all the byproducts are preserved, kernels are preserved, co-kernels are preserved, and moreover the additional benefit is you can treat them as modules. Any questions so far? Okay. So then we can start talking about a new topic. You want to say something? We can start talking about a new topic once we have established the role of Grothendieck categories. Module categories are really good and they have very nice properties. And here is a very popular topic as well. Normally when people study category theory, they either study it for the purpose of algebraic topology or algebraic geometry, which mainly focuses on homological algebra and sheaf theory. So homological algebra is very well developed branch of mathematics. You can say that it's a, we are saying algebra here because we are always going to talk about module categories thanks to Freyd-Mitchell embedding theorem, but we are going to do it more categorically. Now, that's our goal in this course. So what is the main object? So let A be an abelian category. We are not going to say anything more, just abelian is sufficient. First definition that we need, like if you want to define homology or cohomology, you might have heard these terms already. So the first definition is that of a chain complex. So, I mean, okay, maybe I shouldn't say anything like this. If C is small, if C is a small category, yeah, then the functor category, and ever since we started talking about pre-additive and additive category, the functor category is only about, I mean, if whenever appropriate, then we take additive functors. Huh? Functor category to abelian groups. But here I am saying the functor category for a change, I am not taking any restriction on C to be pre-additive. Then the functor category CA is also abelian with pointwise limits and co-limits. Okay, so functor I mean, we have seen such thing earlier. Whatever limits exist in the target category, you can equip the functor category with that, and similarly for co-limits. So this was just a recall. Okay, now do you all understand the set Z of integers? Yeah, with less equal as the morphism. So Z less equal is a category. So is Z less equal op. So Z bigger equal. Okay. Now a chain complex is a functor, I will call it A dot, from Z op to the category A, such that, I mean such that d square is equal to 0. I have to write this. Yeah, so what is happening, that we are taking, it's a sequence of objects and morphisms like this. Okay, and this morphism we usually denote it by dn plus 1, this is dn, and then next one will be dn minus 1, and so on. So such that d square is equal to 0. D square is the composition of two consecutive ones. Yeah, so dn plus 1 composed with dn is equal to 0. Sorry, dn composed with dn plus 1 is 0 for all n in Z. A chain complex is simply this. You have to choose one map from an to an minus 1. An minus 1 are all objects in A. And we are choosing one morphism, and this d square equal to 0, make sure that we are talking about a local thing. There is no dragging effect. Yeah, an plus 1 doesn't affect an minus 2 in any way, or even an minus 1. If I take an element from an plus 1, because I can talk about it thanks to Freyd-Mitchell embedding theorem, then its image under dn plus 1 followed by image under dn is 0. So after two steps, everything becomes 0. So this is called a chain complex. And you can see what I am doing is I am using Z op. If I make a small change, yeah, so a cochain complex, you write these indices at the top and you take this, and the condition is exactly identical. So the lower dot represents that the indices are decreasing. That's why Z op. Yeah, A3 will come first, then A2, A2 to A1. Whereas A upper dot, the cochain complex, is the indices are increasing. It's just a choice. They are isomorphic but not equal.
They are equivalents of category.
There is an equivalence of categories, but here we are more concerned with whether they are equal or not. So we will have a decreasing sequence A3, A2, A1, A0, A minus 1, but there it is increasing A upper minus 1 to A upper 0 to A upper 1.
N and N off would have made sense, but like we are just like shifting the convention here, right?
We are just shifting the convention. Yes, and that's precisely the difference between chain and cochain complexes. Abstractly, there is no real difference, but it depends on applications. So normally, you do not want to work in positive or negative coefficients. Yeah, so depending on that, so for example, if you are doing simplicial homology, then you only define it in positive terms, and then the maps are in decreasing order. So you'll have A3, A2, A1, A0, and then A minus 1, A minus 2, etc. are all 0. So it's a choice, yeah, whether you want to call it a chain complex or a cochain complex. There is very little difference between them. Any questions about this? This is an important concept. And let given any two chain complexes, in this course I am just going to talk about chain complexes, but you can obviously dualize all the results and get them for cochain complexes. Add co. A morphism between them is a tuple Fn from An to Bn, where n is in Z, of morphisms in A such that the diagram commutes, the following diagram commutes. Well, nothing fancy going on over here. Yeah, all these squares should commute. If you want to be very pedantic and very careful, then you will call them something different. So I will show you how to be more careful. You will say that this is dn plus 1a, this is dna, etc. and this is dn plus 1b, dnb. But once you get used to it, you stop worrying about these subscripts and superscripts and you simply call it d. Okay, so such that all these rectangles commute, or commutative squares, not necessarily rectangles. We can think of them as squares, subject to my drawing skills. Okay, so these are chain complexes and morphisms between them, and then the category of chain complexes is denoted, it is a subcategory of Z of A. It is denoted CH dot A. Simple notation, chain complexes. If you want to write cochain complexes, then you will write CH upper dot A and the indices are increasing. Okay. Now the first result that we are going to prove today is phi lemma. I will tell you why it is called phi lemma. And here I am not actually going to use chain complexes and cochain complexes explicitly. I am only going to use their truncations. There is also 6 lemma, 7 lemma, etc., but I am not going to cover them. Let me state what I want to say. So given a commutative diagram with exact rows, okay, let me draw that commutative diagram: A1, A2, A3, A4, A5, and I should stop because it's 5 lemma. Then B1, B2, B3, B4 and B5. And vertically I have some morphisms and I need to label all these morphisms. I'm calling this A1, A2, A3, A4. Then B1, B2, B3, B4. Then the vertical maps I'm calling F1, F2, F3, F4 and F5. Okay. So let me state the exact result, that if F1, F2, F3, F4, if F2 and F4 are isomorphisms and F2, F4 isos and F1 is epi and F5 mono, then F3 is an iso. Okay. Now, out of the blue, why am I talking about these things? But you have to bear with me for this. Yeah. So you want to prove that something is an isomorphism. These results are the foundations of the more complicated things that we build in homological algebra. 5 lemmas, snake lemmas, 7 lemma. Yeah, these are really important. I will show you an application also. So what I am saying is that F1 is an epimorphism, F5 is a monomorphism, and F2 and F4 are isomorphisms. Then F3 is an isomorphism. Okay, do you remember balanced categories? Are abelian categories balanced? Yes, so therefore, if we are able to show that F3 is a mono and F3 is an epi, then I will show that F3 is an iso. Okay. All of you agree? And I am going to use, there are 6 assumptions here. 6 hypotheses that F2 and F4 are iso, which means they are both mono and epi. And F1 is epi, F5 is mono. I will use exactly half of them to conclude that F3 is a mono. Okay, so let me write that. In the proof, we will show that if F2 and F4 are mono and F1 is epi, then F3 is mono. Then what do we use? Once I have done this, then we use the duality principle. In the dual diagram, I will have exactly the dual hypothesis, and that will conclude that F3 op is mono, which means F3 is an epimorphism. Okay. So it's sufficient, thanks to the duality principle, it's sufficient to use half of the hypothesis to conclude half of the conclusion. Good. Now you have to bear with me for some time. I am going to draw a massive diagram, relatively massive diagram, same diagram, but I will extend it. And I will try to explain everything orally. This is the fun part. This is called diagram chasing, and normally people who do not study category theory as a subject, they feel category theory is all about diagram chasing like this. Although you have seen that that is not the case. Yeah, you need to do more mathematics. Okay, so this is our diagram. Let me label these things A1, A2, A3, A4, then F1, F2, F3, F4, F5, and B1, B2, B3, B4. By the way, I forgot to say something. Yeah, maybe I should say that before we start with this. So I said d square is equal to 0 in the definition of a chain complex. What does that mean? Image of dn plus 1 is contained inside kernel of dn. Yeah, but I mean in category theoretic language, the subobject image dn plus 1 is smaller, is less equal the kernel. And if it is exact, then they are equal. Okay. So we are given this particular setup. And we are going to use that F2 is a mono, F4 is a mono, and F1 is an epi. So this is our given setup, and I am going to use a different color. If you can use a different color as well in your notebooks. Okay, now what do we need to show? F3 is a mono. What is an equivalent condition for F3 being mono in the language of abelian categories?
For any two parallel morphisms.
Any two parallel morphisms, we don't use that. We show that its kernel is 0. So let me start by writing the kernel. Okay, this is my capital K3 with little k3 as the arrow, the kernel of this. I'm not going to do any writing, I'm just going to build a diagram. Okay, so now observe that F3 K3 is 0. So therefore B3 F3 K3 is 0, but B3 F3 is F4 A3. This diagram is commutative, this particular square is commutative. So K3 first, then A3, and then F4 is 0. But F4 is mono. So therefore A3 K3 is 0. But what does that mean? That K3 factors through kernel of A3. Yes, you agree? K3 factors through kernel of A3. But what is kernel of A3? It is image of A2. Okay, so now let me draw the new piece of information. So this image of A2, that is I2. Then there will be a surjection. This is the co-image of A2, and this will be the image of A2. So I know that there is a factorization like this. Okay, this is, sorry, I wrote A2 here, I wanted to say image of A2. And the object for the image I am writing is it as I2. Then I will construct a pullback of this purple diagram only. Okay, and I am going to call this K2, I will call this little k2, and this one I will call E2. Okay, I don't really worry about the other map. Then recall that pullback of a mono is always mono, but in an abelian category, pullback of an AP is also an AP. So therefore, yeah, I mean this is a pullback. So I can conclude that E2 is an epimorphism, because E2 is the pullback of this co-image of A2. Co-image is an epimorphism, so its pullback is epimorphism again. Okay, so far so good. Are you still with me? Yeah. Okay. Now consider B2 F2 K2. So B2 F2 K2, what is it? Or maybe I should write a little bit, otherwise everything will be lost. So B2 F2 K2 is, I mean, okay, maybe I won't. B2 F2 K2 is same as F3 A2 K2, and if A2 can be factored like this. So therefore, what I am saying that F3 then image A2, then co-image A2, and then K2 is 0, which I can factor like this. Yeah, instead of going along this path, I can go like first do E2, then go to I2, then come to A3 and then do this, which means it is same as doing E2, then K3 and F3. Understood? A2, K2 is A2, K2 is K3, E2. And then when I compose it with F3, then F3, K3 is 0. Yes, so therefore B2, F2, K2 is 0. B2, F2, K2 is 0. That means F2, K2 must factor through the kernel of B2. Well, what is the kernel of B2? It has to be image of B1 because we are given an exact sequence. So let me call this J1 and this is my image. I never said that. I never said that K2 is kernel of F2. I just said that K2 is the pullback. Okay. Huh? We will see lot of things. So far you agree with me that F2, K2 factors through J1 and this image B1. Huh? But I never said F2, K2 is 0. I said that B2, F2, K2 is 0. Therefore, F2, K2 factors through image of B1 equal to kernel of B2. Okay, so now this is the factorization. Then I'm going to highlight using a different color these four objects, these three objects. Take these three objects and then construct a pullback around this. So I will get a K1, then I will have a map namely E1, and then I will have a map to A1. This one I will call little K1. Okay. Then A1 to J1, we are using that F1 is an epi and co-image B1 is an epi. So their composition as an epimorphism. So its pullback has to be an epimorphism. So E1 is an epimorphism. K1 is the pullback of the green diagram, green highlighted diagram. Okay. Are you still with me? Do you want me to repeat any argument? So as soon as you understand that B2, F2, K2 is 0, so therefore there is a factorization of this F2, K2 through image of B1. So there is a map from K2 to J1 and then I am taking this pullback. Okay, what can we conclude from here? Well, now K2 E1 is equal to, can we say anything about K2 E1? No, we haven't yet used anything else. Okay, so maybe now I should write something. Okay, so B1 F1 K1. What is B1 F1 K1? Yeah, I mean B1 can be factored like this, and then F1, B1 F1 is also this, but we don't want that. Yeah, we want to reach this point, but we are going to take the path via J1. So therefore, we are coming from here to B1, K1 to A1 to B1 to J1 to B2. That is this map, which is same as K1 to K2 to J1 to B2. Correct? Because the inner thing is a pullback diagram. So K1 to K2 to J1 to B2. That's our diagram. But this outside thing, like when you compose it with image B1, you actually get F2K2. So F2K2E1. Yes? Any questions so far? Okay, so this is one thing that we need. And another thing that we will need is we have to look at A1, K1. Okay, so A2, A1, K1 is what? So B1, now notice that B1, F1, K1 is same as F2, A1, K1. And we showed that this is also equal to F2, K2, E1. Okay, so now because F2 is a monomorphism, so we can conclude that A1, K1 is equal to K2, E1. Yes? A1, K1 is K2, E1. No, we never said it's a pullback or push out. We just take the pullback of K2, J1 and A1. So now we have concluded that the top diagram commutes. So A1, K1 is equal to K2, E1. Now substitute that over here. So A2, A1, K1 is A2, K2, E1. But A2, A1 is 0 because it's a chain complex. So therefore this is 0. And since E1 is a mono, E1 is an epi, what do we conclude? That A2, K2 is equal to 0. Well, what does that mean? A2, K2 is same as K3, E3. K3, E2. Correct? A2, K2 is same as K3, E2. And well, E2 is an epimorphism. So therefore, this will conclude that K3 is equal to 0. And this is the end of the proof. K3 is 0, which means kernel of F3 is 0, which means F3 is a mono. Any questions? E2 is epi because it is the pullback of co-image of A2 and pullback of epi is epi. Yeah, we are working in an abelian category, so things work. Yeah, it looks like a very long proof, but this is called diagram chasing using arrows. Okay, let's do another proof like this. These are all 2's, okay? In homological algebra, you cannot live without doing these 2's. And the next one is called snake lemma. In fact, if you study, let's say, algebraic geometry, then people will tell you that abelian category, you don't need to know the definition. Abelian category is any category in which snake lemma holds. Okay, this is the foundation of homological algebra. Yeah, very beautiful result. I don't know who came up with it. Now it's just called snake lemma. But observe what is happening. Yeah. Given a commutative diagram with exact rows and columns, I mean, maybe I should say with black arrows, yeah. Given a commutative diagram with black arrows, with exact rows and columns, there is a green sequence. There is an exact green sequence. Okay, so exact rows and columns, let's see what I mean by that. So we are given A1, then A2, then A3, and then 0. Okay. Then here we are given 0, B1, B2, and B3. Here we are given F1, F2, and F3. Then here we are given the kernel. Yeah, this is the kernel of F1. Then K2 is the kernel of F2, and K3 is the kernel of F3. Simultaneously, Q1 is the co-kernel of F1. Then Q2 is the co-kernel of F2, and Q3 is the co-kernel of F3. Then obviously, because I am talking about kernel, then this becomes augmented with zeros so that the vertical sequences are exact. Okay, so this is the given diagram, the black diagram. And the exact sequence that we are talking about, it comes here. There is an arrow from K1 to K2, K2 to K3, and Q1 to Q2, Q2 to Q3. Moreover, there is this long snake-like arrow, which is called the connecting arrow, from K3 to Q1. And this snake-like arrow, this snake-like diagram is what makes people call it the snake lemma. And you can see that we started with two exact sequences. Yeah, let me name them something. Let me call this is A1, this is A2, this is A3, this is A4. Sorry, this is B1 and this is B2. And this one is, let's say, E1, E2, and this is T1, T2. Okay, so if we are given these many hypotheses, then there exists a green exact sequence. The beauty of it is that you connect the sequence of kernels. Yeah, it's not very hard to show that K1 maps to K2 and K2 maps to K3. The kernels appropriately have to map. Now that's not hard part. But there is a connecting arrow between kernel of the last map with the co-kernel of the first map. This is the most beautiful part in this. And this 6-term short exact sequence exists. Moreover, yeah, I mean, this is an extra thing. I'm going to use violet color. If there is a 0 at this point, then there is a 0 at this point. If the first sequence is exact, if A1 is mono, then E1 is mono. And dually, if B2 is epi, then T2 is also an epi. So then, given two short exact sequences, perfect short exact sequences, you will get an 8-term long exact sequence of kernels and co-kernels. Okay, any questions about this? So this is, yeah, I mean, these ones, now as you can imagine, if the statement itself contains this size diagram, then how much we will need to do with the proof. Yeah, so there are many steps in the proof, but for the purpose of this lecture, I am going to be content with only the description of the map delta. Exactness I will leave as an exercise. Okay, or constructing E1, E2, T1, T2, that also I will leave as an exercise. So I'm just going to talk about this delta map. Okay. So let me use a different color. I have this facility, and then I will show you how to take this element. So let us start with an element x in K3. Now here is the second method of proof. We are only going to talk about so many objects. So I can always work with the small abelian category generated by these objects, and that will be small. So it can be embedded in a module category, so I can treat everything as an element, as a module, and therefore elements. So let's start with an x in K3. Then where does this x go? Well, I can say it's K3x, but it's an injective map. So I might as well call it just x. It doesn't matter. If I go down, then what will happen? I will reach 0 because it's coming from the kernel of that map, kernel of F3, so it will be 0. Which means, and moreover, this little a2 is an epimorphism. So therefore, this K3x must come from some y in here. And that y has the property that when you go to K3x and down to 0, then therefore, if you go below it, yeah, f2 of y, then f2 of y also maps to 0 because it is a commutative diagram. So f2 of y is in the co-kernel of B2, right? It is in co-kernel, sorry, it's in the kernel of B2, and kernel of B2 is same as image of B1. So image of B1, which means there is something z, some z here, which maps to f2y. So B1 of z is f2 of y. Okay, and then this z I can send it to Q1z, and that becomes my delta of x, Q1 of z. However, yeah, I cheated at many points. What is the cheating? That I made a choice, right? So x to K3x, everything is okay, but y, I made a choice of that. Yeah, I also made another choice, z. So what to do with z? Z is not a problem because B1 to capital B1 to capital B2, the little B1 map is injective. So if it belongs to image, then there is a unique element. So I don't have to worry about little z. But I do need to worry about the choice of y. Yeah, y was my choice. So Q1z depended on my choice. Well, that's not a map. It's not a well-defined map. X mapping to Q1z is not a well-defined map, unless I show that it doesn't depend on my choice. Okay, so what will happen if y and y prime are both elements in A2 such that little a2 of y is equal to K3 of x equal to little a2 of y prime? If both of them go to the same element, then what will happen? Well, therefore, because we are working in an abelian category, so a2 of y minus y prime is 0, which means it belongs to the kernel of a2. Well, kernel of a2 is the image of a1, but image of a1, I mean, basically what I get is that there exists some w. So therefore, there exists some w in A1 such that what happens? A1w is equal to y minus y prime. Very good. Okay, then now we are worried about f2. So what will happen with f2 of y minus y prime? This will be same as f2 of a1 of w. Yeah, but F2A1 is B1 F1, B1 F1 of W. So therefore, what did we conclude just now? F2 of y minus y prime belongs to, B1 is injective. So we actually concluded that whatever choice we might have made, F1 of W is Z. Yes, yes, yes. No. No. So therefore, F2 of Y is B1 of Z. F2 of Y is B1 of Z. Yeah. Minus F2 of Y prime is equal to B1 of F1 of W. So basically, we got an expression for f of y prime in terms of this. But when we quotient out by anything, see this little q1 is the co-kernel. So co-kernel, which means we are mapping to the coset. Yeah, in that coset, anything which comes from A1 gets identified. Anything which comes from capital A1 gets identified. Yeah, so look here. So capital A1, W is coming from capital A1. So therefore, its image under this little q1, like F1 of W under little q1, that's not going to matter at all. Okay, so therefore, what I'm saying is that q1 of F1 of W, but q1 of F1 of W is equal to 0. And therefore, it doesn't matter what choice you make. Yeah, you will have Z and correspondingly you will have a Z prime, but q1 of Z will be equal to q1 of Z prime. Okay? So therefore, it doesn't really depend on my choice. The entire exact sequence is taking care of this. So that's called snake lemma. Any questions? Like I just defined this connecting map, snake map delta, but you had to verify that it is exact at every single step. And
So you said that any category which has
snake lemma is
a variable, right?
see, that's a heuristic. I'm not saying that is the definition, but in practice, that's how people think. That any category in which snake lemma holds is called an abelian category. You don't need to worry about the definition of an abelian category. It uses the full strength of an abelian category.
There are exact sequences there which are only defined if that category is complete.
Yes, I totally understand, but it's a heuristic. Yeah, so we don't really have to worry about it. Well, I will.
We can still
Huh?
define kernels in a probably a pre-additive category. So can we say that if a pre-additive category follows snake lemma, then it follows this?
No, it's not a perfect statement. Yeah, we don't want to say that we are given a pre-additive category. You can't define kernels and co-kernels. So basically, the setup for the snake lemma is an abelian category, and whenever, it's not a perfect statement. Okay, that's all you need to remember. But in practice, people don't want to define an abelian category formally. So they will say that just work with this and modules, you are fine. Okay, before ending this lecture, let me define the titular object of homological algebra, namely homology. Okay, so let's do that. So suppose A dot is a chain complex over an abelian category for an abelian category A. Okay. The nth homology of A dot denoted Hn of A dot is defined in two equivalent ways. As follows. Okay, the first and the classical definition that people think about is this, yeah, that okay, you are given this exact sequence an minus n plus 1, then we have an, then we have an minus 1 and so on, then we have this an plus 1 and we have an, these morphisms. The classical definition says that you construct its kernel, yeah, because we know that the kernel, this is kernel, so I am going to call it kernel of an, and I am just going to call this Zn. So the term Z is used for the German word for cycles. Okay. So Z is always like the elements of Zn are called cycles, whereas the elements of Bn, which is the image, these are called boundaries, not cocycles. Cocycles come for the dual version, cochain complexes, cocycles and coboundaries. But Bn is the image of an plus 1. So we always know that Zn and Bn, yeah, one thing embeds into another because it's a chain complex. So an composed with an plus 1 is 0. So therefore there must exist a factorization, and because kernel of an is a monomorphism, this factorization is unique. Okay, whatever is this particular map, let me call it Sn. So classically, if you take co-kernel of Sn and then you define the object for that is called the nth homology. So what is it doing? It's trying to measure the extent to which this sequence becomes, this chain complex fails to become exact at nth location. If it were exact, then Bn and Zn would be isomorphic. So therefore Sn is an isomorphism, its co-kernel will be trivial. Okay, so homology is the measure of failure of exactness at nth point. So this is the traditional definition. But if you want a more symmetric definition, yeah, so it is just a note, it's measure of failure of exactness at nth location. And the symmetric definition, more symmetric definition that I can talk about, I am just going to draw the same diagram again because we are not doing anything different. an minus 1 and so on. Okay. So here we take the co-kernel of an plus 1, and this object I am calling Qn. And the object over here, I am still calling the kernel as Zn cycles. So this is kernel of An. Now you consider this composition from Zn to Qn. Yeah, first embed into An and then quotient out up to Qn. The image factorization, the image object for this is the homology. Okay. So this is called Hn, where this is the image of co-kernel An plus 1 composed with kernel An, and this is the co-image of co-kernel An plus 1 composed with kernel An. So Hn is the image factorized, the image object in between. And this is a symmetric definition. Yeah, we want a symmetric definition. Everything happening is symmetric. Okay, so it is the measure of failure of exactness at nth location. These two definitions are equivalent. I will give it to you as an exercise. And let's stop for today.